All right, guys, so we are finally on the last unit for this course. If you haven't noticed already, Unit 6, the last one in APEX, does have graded material, but it's all preparation for the AP exam. So this will be the last set of actual lessons you'll have to learn. And then from that, after that, it's just review. So let's get into it. The first section here, 5.1, is going to be making more inferences based on data. So we're going to do hypothesis testing and confidence intervals like we have been doing. But this time we're going to go back to categorical type data, and we're going to go away from the distributions that we've seen before and look at a new distribution. Okay, this distribution is called the chi-square distribution. The chi-square distribution. So the chi-square distribution is really helpful for when our variables can take on more than two values. So everything we've looked at before this has all our possible outcomes have been success and failure, and those have varying meanings, but in everything we've done inferences on so far, our possible outcomes were just success and failure. So now we're going to look at scenarios where there's more than just those two possible outcomes. What is that going to look like? So the chi-square, you can see how it's spelt there. This is going to be the statistic we're going to use to make these inferences. You can see here how it is calculated. The epsilon here, or the sigma here means that we're going to add up each of these for each different outcome. Okay, so we'll see lots of examples of how that works. So chi-square, the symbol for it is this Greek letter chi. It's like kind of like a cursive looking X with a square. So this symbol, the cursive looking X, is actually a Greek letter chi squared. It represents the population statistic, population, or the parameter. So, and then of course we know when we're making inferences, we don't know the values of the true population. So we estimate those, that's the whole point here. We estimate them using a statistic. A statistic is based on a sample. So the statistic version of chi-squared is just a regular capital X squared. So when you see the cursive looking chi-squared, that means we're referring directly to the population. And if you see the regular print capital X squared, that's still chi-squared, but here we're talking about the sample. And remember, when something is taken from a sample, we don't call it a parameter, we call it a statistic. There we go. Okay, so that's some major notation differences there you're going to need to make sure that you be careful of. Kind of like how with means, we use mu for the population and we use x bar for the sample. For standard deviations, we used sigma for the population and we used s for the sample. The same thing here. That's why there has to be a difference. So we know what we're looking at. Okay, and just like with the t-distribution, the chi-square distribution is going to depend a lot on these degrees of freedom, which is still abbreviated with a df. This time, though, the degrees of freedom is determined by the number of possible outcomes minus 1. So previously in the t-distribution, it was the sample size minus 1 was our degrees of freedom. In this one, we're looking at scenarios where we have more than two possible outcomes. So our degrees of freedom is going to be the number of possible outcomes minus 1. And just like in the t-distribution, the chi-square distribution is going to look slightly different for each degrees of freedom. So there's actually a totally different chi-square distribution for each number of degrees of freedom, just like there was for the t-distribution. So in the chi-square distribution, the chi-square statistic, chi-squared, will always be non-negative. And the reason for that is because if you look at the formula we use to get chi-squared, we have to square all of our values. And as you know, when you square any number, the result is always positive. Okay, a negative number squared is positive. Positive number squared is positive. 0 squared is 0, which is still non-negative. So we will never have any negative numbers in our chi-square distribution. If our data fits the expected values perfectly, the chi-square statistic will actually be 0. So what we're going to do with this chi-square distribution is we're going to compare the values that we expect to get for our different outcomes to what we observe in a sample. So if our sample fits what we expect perfectly, then observed minus expected will be 0. So our chi-square statistic will be 0. That also means that the larger our chi-square statistic is, that means there is more differences between our observed and our expected values. So the more different our sample is, the larger our chi-squared is. So we can imagine rolling a die over and over and over and over again. We've talked about this before. You would expect to get each number on a die 1/6 of the time. And so if I rolled my die 100 times and I got each number exactly 1/6 of the time, my chi-square statistic is going to be exactly 0. But if for some crazy reason I roll a die 100 times and I only get like odd numbers and no even numbers, that seems really fishy, right? That seems highly improbable. And because of that, our chi-square statistic is going to be a large number, which is going to indicate to us that something is rigged here. Something is not being done by chance. Okay, and that's exactly how our inferences are going to go. So the chi-square distribution itself is actually going to be right skewed. So this one is not symmetrical. Remember, we said the chi-square distribution will always, the chi-square statistics will always be non-negative. So they could be 0 here, but they're never going to be a negative number. For good samples, if we do follow our true expected values, we're going to expect our chi-squared to actually be 0. More often than not, though, our chi-square is going to have a little bit of size to it, right? It's going to be pretty rare to see a sample that fits our expected values perfectly. But we would hope we won't see a chi-square statistic that's very, very large. So what we get is okay, it's possible to get 0, but not likely. It's way more possible to get a slight difference in our observed and expected values, but it's not very probable to get these larger values. So you can see it is a right skewed distribution. Okay, and you have a table, a chi-squared table. It's in the set of tables you should have got at the beginning of the year, along with your Z table and T table and your formula sheets. Remember, your Z table, your T table, your formula sheet, and this chi-squared table will be provided to you for all parts of your AP exam. And they should look, from what I've seen in the past, identical to the ones that I gave you. So if you open that up, here's my chi-squared table. It looks just like this. You can see again, it is right skewed, all positive. And remember also too, if you have lost your formula sheets or your table sheets, I provided an extra copy on Google Classroom under the resource tab. And if you have trouble finding that, let me know. Okay, so this table works very, very similarly to the T table. Just like the T table, on the left-hand side, we have our degrees of freedom. And on the top, we have our upper tail probability. This is actually the upper tail probability. So both the chi-square distribution and the T distribution give you the upper tail probability, whereas the Z table gives you the lower tail probability. And you can see that it's indicated on the part that is shaded in each of these tables. So you can see these probabilities, these decimals up here are the probabilities of getting a value greater than the indicated statistic, also known as the area under the curve above that. Okay, so when I connect the dots here, all of these values inside of this table here are the actual chi-square statistic. And as you know, when we need those critical statistics to calculate our confidence intervals and such. Okay, so going back to our notes, the distribution of chi-square depends only on the degrees of freedom. So as we said, there's a different distribution for each number of degrees of freedom, just like in the t-distribution. The mean, this is interesting, this part, the mean of the chi-square distribution, remember that's the center of our distribution, which is it's skewed, it'll be somewhere around here. That mean of the chi-square distribution is the number of degrees of freedom. How weird is that? Okay, and the variance, remember variance is the standard deviation squared. The variance of the chi-square distribution is equal to twice the number of degrees of freedom. So if we have a chi-square distribution and we know our degrees of freedom is, say, 5, meaning there's 6 different observed values, then we would know the mean of our chi-square distribution is 5, and we would know the standard deviation of our chi-square distribution is 10. The square root of that being, or sorry, the square of that, no, that's variance. The square root of that 10 being the standard deviation of the chi-square distribution. So that makes things a lot simpler, but we're actually not going to even need that too often. So here's a small clip of that chi-square distribution I showed you on that other page, and you should definitely have that handy. So as I already said, we got our degrees of freedom on our column here. And then each of these values on the top, which obviously there's a lot more than just these ones, those indicate the upper tail probabilities, which means all the numbers in the actual table are the actual chi-square statistics themselves. Okay, so if I was doing a confidence interval, maybe I was doing a 95% confidence interval, that would mean that I would want my upper tail to be 0.025, right? Half of 0.05. And maybe the number of possible outcomes was 7. So I would want degrees of freedom 7 minus 1, 6. That means the chi-square statistic we're going to use is, follow them over and down, and we get 14.45 for our chi-square statistic. Okay, there is also some chi-square options in our graphing calculator. Let me show you that. There's not as many as there are for the z and t distributions though. So if I go to my distributions menu here, second vars, remember we had our normal CDF and PDF that would give us the probability between two values, or the probability of one value for PDF. An inverse norm would give us the actual statistic based on the probability. TCDF gives us the actual probability between two values. TPDF gives you the value, or sorry, gives you the probability of the t distribution taking on one specific value. And then inverse t would give you a specific t statistic based on a probability. So with chi-squared, we go down, we only have these two options. We only have the PDF, which gives you the probability that chi-square takes on one specific value, and chi-square CDF, which gives you the probability that chi-square is between two different values. So we can use these, and we're really just going to use CDF, just like we have been for everything else. We can use this to find probabilities, but notice there's no inverse chi-squared on here, no INV chi-squared. So I cannot put in my tail probability like we do in the graph and get the statistic. So if I need to find a specific statistic, like for a confidence interval, I'm not necessarily going to be able to use this menu to do that, like we could with the inverse T and the inverse norm options. So this table is going to be pretty helpful. It's going to be the best thing to use for that. Also notice these numbers on here don't go perfectly. There's a lot of variation, like between here and here, 4.11 and 4.64. And there's a lot of variation between these two. So sometimes you might kind of have to be like an estimate or say, well, this one's closer, and then just go from there. So if I wanted to check this out, previously I said 6 degrees of freedom, tail probability 0.025 gave us the statistic. The only way so far that we could put that in our calculator, I could say, whoops, supposed to be a pen. There we go, chi-square CDF. And I could use the statistic to get this probability 0.025. Yeah, so that's an upper tail. So that means we'd be starting at 14.45 and going to infinity. So I'd put in like 9999999. And our degrees of freedom is 6. So when I put this all in, it should give me the probability is 0.025. So let's just check that out. So I'll just choose chi-square CDF, lower bound 14.45, upper bound 999999999. DF is 6, paste, and there we go. I had 0.025 in my table. Here is 0.02499, which rounds to 0.025. Okay, so that's how that works. I'll chip this in here. It was about 0.02499. Okay. So let's go ahead now and do a significance test. So the significance test, the first type of significance test we're going to learn about that we can do with a chi-square distribution is called the goodness of fit test, okay, which is abbreviated GOF. GOF, okay? And this first one, we're going to start with the easy one. We're going to do a GOF test for when our outcomes have equal proportions. So they give you this example in the video here. Well, first of all, actually, the condition. In order for the chi-square test to be valid for a one-way table, each expected value must be at least 5. Okay, so when we're doing our hypothesis tests, you know, the first thing that we really should do each time, which they kind of skip a lot in the ABEX videos, I've noticed, you always want to start by checking all of your conditions. Okay, so that's going to be the one condition we have to check here. Not a lot. It seems pretty easy. So let's look at this LeSoda thing where she's trying to get the different letters of LeSoda to win some prize. And we would hope that each letter would appear equally. You know, the L, the E, the S, the O, the D, and the A should occur equally. So we're expecting this to be equal proportions, but she's starting to suspect that that's not true because after drinking 120 bottles of LeSoda, these are the amounts that she got. Okay. So let's, first of all, to check our condition, we have to look at our expected values. And we need our expected values actually to calculate our statistics anyways. So let's see, if n is 120 and there's 1, 2, 3, 4, 5, 6 possible outcomes, which by the way means that we have 5 degrees of freedom, right? Take your number of possible outcomes, subtract 1, and that's your degrees of freedom. We're going to need that later on. So if all 6 of these were going to occur at the same probability, then we would assume that each of these would have a probability of 1/6. That'd be 1/6 chance of getting an L for each soda, a 1/6 chance of getting an E for each soda, and so on and so on and so on. So out of 120 in our sample, what would we expect to get for L's? Well, what is 120 divided by 6, or 120 times 1/6? That would be 20. So we would expect in a sample with a size of 120, we would expect to get 20 L's. We would expect also to get 20 E's, 20 S's, 20 O's, 20 D's, and 20 A's. Add them all up, that's a perfect 120, and they're distributed evenly. So our condition, back up here, is that each of our expected values has to be at least 5. Was that met? Absolutely. All of our expected values are 20. Makes that easy to check. And 20, of course, is greater than 5. So we have met our condition. We can go ahead with our significance test. So then we know the next step of our significance test is to state our hypotheses. So we have all, just like always, we have a null hypothesis and we have an alternative hypothesis. Okay, so our null hypothesis is going to be that our expected values are true. And in this case, our expected probabilities is, like I said, we're expecting that they'll all have a probability of 1/6. So we would say we expect that the probability of our first letter will be the same as the probability of our second letter, which will be the same as the probability of our third letter, and our fourth letter, and our fifth letter, and our sixth letter, and we expect all of those probabilities to be exactly 1/6. Another way we could say that is that we're hoping to get a chi-squared number equal to 0. Remember, if our observed values in our sample match our expected values perfectly, which they obviously don't, we're going to get a number exactly equal to 0. So in context, we always have to say that in context. That would mean the letters appear at the same frequency. So you can see there's a bit more to write in here. My null hypothesis is literally for any goodness and fit test, we're hoping to get a chi-square statistic that is close to 0. Or that would be our null hypothesis, would be that it's close to 0. We're trying to disprove that, and of course, hoping it's not true. But I also need to include in my null hypothesis the actual distribution of our expected probabilities, as well as what that all means in context of the problem. Okay, and then my alternative hypothesis is going to go the same way. We're going to say that at least one of these 6 probabilities is not 1/6. At least one probability is not equal to 1/6, meaning that chi-squared, and remember chi-squared always takes on a non-negative number. So chi-squared is never going to be less than 0. In fact, if I just say that chi-square is not equal to 0, then that means that chi-square has to be greater than 0, because again, chi-squared cannot be negative. So our alternative hypothesis for any goodness of fit test will always be this. How handy is that? Anytime you're doing a chi-square hypothesis test, here's your null hypothesis, here's your alternative hypothesis for every single one, which is why we also need to include more specifically what are those actual probabilities, and also even more specifically, what does that mean in context? The letters do not appear at the same frequency. Okay. So again, we've got like one extra thing to write in here, really, this stuff that I highlighted in pink, but it's really not even that big of a deal because you need to know that expected probability in order to check your conditions and in order to connect your statistic. And the stuff I highlighted in yellow will be the exact same for any chi-square test. That saves you a lot of time. All right, so next step, as always with significance tests, we're going to state which test we're going to perform and what our significance level is. So we are going to perform a chi-squared goodness of fit test what this is called. With DF equals, we said 5. At significance level, alpha equals, let's do 0.05 like we normally do. Remember, alpha doesn't have to be 0.05, but that just happens to be the most common one. So important thing in here, just like with t-distributions, there's a different chi distribution for every number of degrees of freedom. So make sure you say which chi distribution we're looking at within the type of significance test that we're doing. And this test that we're doing is called a chi-squared goodness of fit test. When we go to our calculator later on in this section, you will see there are 2 different types of chi-squared test. There's a regular chi-squared test, and there's a chi-squared GOF, goodness of fit test. So we're doing this one, the chi-squared goodness of fit test. Let's go ahead and do it by hand first, and then I'll show you how we can use our calculator to make all of this much simpler. This type of problem, this goodness of fit test, will most likely be given to you on the part of your exam where you're allowed to use your calculator. All right, but it is always good to know how to do this by hand anyways, just in case. If you were to have to do this by hand, it definitely would be a small number of degrees of freedom or a small number of observed values. You'll see why in a second. So to compute this test statistic, we're going to use the formula that was given to us before, and that is sigma, the sum of observed minus expected, squared divided by expected. Okay, so let's do this by hand first. I'll go through it pretty quick because I already have these numbers written down, but you'll be able to see the process. So I'm going to go ahead and write this fraction down for each letter in Lesotho. So for L, we observed 31, we expected 20, and I'm going to add up each of these for each letter. So for E in Lesotho, we observed 10 and we expected 20. And again, these numbers are just coming from this table here. There's my observed in the actual table, and I wrote the expected right below to make it convenient. Now I'm going to add to that. For S, we observed 25. We expected 20. For O, we observed 32 and expected 20. For D, we observed 15 and expected 20. And finally, for A, we observed 7 and expected 20. So you can imagine the more possible outcomes you have, the longer this initial formula is going to be. Again, there's a lot of different ways that we can make this faster on our calculator if we're allowed to use that on that portion. So each of these individual fractions, I got them. For L, it ends up being 6.05. For E, it ends up being exactly 5. For S, I got 1.25. For O, I got 7.2. For D, I got 1.25 again. And for the letter A, I got 8.45. So when we add those all up, we get a chi-square statistic, which I should use a new print chi-square, because it's a statistic, of 29.2. In fact, up here as well, this is a statistic, not a population parameter, so that should really be a print x, not a Greek letter x. It's kind of a habit. So that is our statistic, our chi-square statistic, and it didn't take too long to calculate there, honestly. I mean, I obviously did some little bit of math magic for you, but there's only 6 observations here, so it's not too horrible to do by hand. Okay, now continuing by hand, with any significance test, we're now going to calculate our p-value which is the probability that chi-square is, looking at our alternative hypothesis, always greater than, so greater than the number we just calculated, 29.2. Okay, so another nice thing about chi-square tests is this will always be a greater than symbol as well. Okay, so I could of course use my calculator for this, but let's go over how to do it by hand first. Actually, I don't know. So on your, I don't know that we really can do this for sure by hand, but we can look. So let's look at our thing. We're gonna find greater than 29.2. So again, on this one, it doesn't give our statistics as a possible value. So I gotta look in this table for 29.2. Our degrees of freedom was 5 though. So we're only looking at this row here. Now my piler's a little chunky, but we're only looking at that row right there. And we're looking for the number 29.5. All right, and so we can see that 29.2 is nowhere near here. The biggest number we have, and notice it does go from smallest to largest, is 20.51. So we're looking at a number that's definitely way further this way, which means our tail probability, unless going from greater to less, our tail probability is going to be way less than 0.001. So if I did not have a calculator here, the best I would be able to say is that our p-value is much less than 0.001. Which is actually good enough to reject our null hypothesis. Because remember, our significance level was 0.05, and if we're less than that, which we definitely are, less than that, then we can reject our null hypothesis. We don't need an exact p-value, we just need to make sure it's less than 0.05, okay? But since we do have our calculator handy, let's go ahead and see what that exact p-value is. So on my calculator here, I'll use that chi-CDF to find that range, that p-value. So that is my option 8, chi-CDF. Make sure you don't choose PDF by accident. My lower bound is going to be this 29.2. My upper bound is 9999999, or close to as close to infinity as I want to do on my calculator. And our degrees of freedom this time is 5. So that tells me my p-value, see it's got this e-5 at the end. That means I'm going to take this decimal and move it 5 spaces to the left. So it'll be about 0.0000402, which is very, very, very small. And like we said, it's definitely less than 0.001. So we can now go ahead and state our conclusion. Since our p-value is less than alpha, we reject our null hypothesis. In context, what does that mean? Rejecting our null hypothesis supports our alternative hypothesis. So we can say this, the letters don't appear at the same frequency. There is enough evidence to conclude that the letters do not occur at the same frequency. Ta-da! All right. Okay, and then one more thing going back here. If we have access to our calculator, there's an even faster way we can do this part. As we've seen before on our calculator, if I go into the stat menu, move over to tests, I have the option to calculate exact confidence intervals or exact statistics and p-values when doing a hypothesis test. So if you scroll down, we've used a lot of these already. We see our chi-squared test, and we're doing a chi-squared goodness of fit test. So I'm choosing my option D. And you want to see when I choose that, it asks for my observed and expected values, and then they are asking for lists. So that means before I can ask my calculator to do anything here, I need to go to my stat menu, click edit, And I need to fill in this list with my observed values and this list with my expected values. So let's go up and look at what those were. There they are. My observed values in my given table was 31, 10, 25, 32, 15, and 7. 31, oops, can't see them. 10, 25, 32, 15, 7. And our expected values, of course, were all 20. Okay, so now that I have my observed values in list 1 and my expected values in list 2, I can go back to my stat menu, over to tests, down to my option chi-square GOF. And of course, if you had my data already in different lists, I can change those very easily by clicking second and then the number of the list that they are in. Okay, but they are in list 1, so I'll hit second 1 back, and list 2. Degrees of freedom here is 5, so I don't need to change that. And then I hit calculate. Remember, draw should give you the same numbers, but also with a nice picture of what that looks like. And it's a great idea to include pictures of the curves with the shaded area on your AP exam. It'll earn you some extra brownie points. So I hit enter, and there we go. There's my chi-squared statistic, 29.5. Exactly, we got 29.2, is exactly what they have here. And again, the p-value, 0.00002, exactly what we had here. So the exact same answers on our calculator. It took a little more time to go ahead and put those data points into our lists, but after that, no big deal. So if you're allowed to use your calculator on this question, this may be the fastest way to get your answer. Okay, now let's look at an example where we're doing the same thing, but this time the proportion for each observed value are unequal. It's no longer 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. This time, we're expecting 10% of the school body to wear the mascot, 30% of the school body to wear colors, and 60% to wear neither. So, what would our expected values be? They're taking a sample this time of 75. Okay. So, what is, as we said, 10% would wear the mascot. So, what is 10% of 75? So take 75, multiply it by 0.1, we get an expected value of 7.5. We also expect to have 30% that wear school colors. So what is 30% of our sample? 75.3 times 75 gives us the expected value 22.5. And for neither, we expect 60% won't wear those school colors. So what is 60% of our sample? 75. 0.6 times 75 is 45. So there's all my expected values. So now we can use that to check our condition. Are all of our expected values greater than 5? Yes. Our expected values, 7.5, 22.5, and 45 are all greater than 5. So yes, we've met that condition, so we can continue. Let's state our hypothesis. As I said before, our null hypothesis for a GOF chi-squared test is always going to be that that is 0, or at least very, very close to 0, right? We're hoping that any variation from that is only due to chance. And our alternative hypothesis will always be that chi-squared is greater than 0. If it's not 0, it has to be greater than 0 because chi-squared can never be negative. So what does that mean for the proportions? If chi-squared equals 0, then that means our proportions are exactly what we expect. P1 is exactly 10%, P2 is exactly 30%, and P3 is exactly 60%. Which means in context, 10% wear the mascot, 30% wear school colors, and 60% wear neither. Don't have enough room to really write a full sentence there, so I am kind of abbreviating still. Just for an actual test, I would definitely want a full sentence. Okay, and what are we expecting of our proportions if chi-square is significantly greater than 0? Well, we would be expecting that at least one of these proportions is not true. So at least one of these proportions, which I get weird handwriting here, of these proportions is different. Okay, so there it is in context. There's not really any way to put that in equation form, so that's basically it. Covered up, checked all the boxes. All right, so let's compute our test statistic and p-value. Okay, and just for the experience of it, I'm going to go ahead and do it by hand as well as with my calculator here. So my chi-square statistic, again, is the sum of all expected values minus observed, minus the other way around. Observed minus expected squared divided by expected. Notice I abbreviated that time. The book does too. So I only have 3 observed values here. So this is very short. This is definitely one that we can do by hand. So my observed values for school mascot is 11 minus expected was 7.5 over expected. Add that to colors was 26. We expected 22.5. It's pretty close. And for neither, we saw 38 and we expected 45. That is a bit different. So we follow order of operations, and we should get that that statistic chi-squared is about 3.266. So we can try to do this from our table again, remembering our degrees of freedom is a number of expected values minus 1. We have 3 observed values, so that would be 2. So going to my table right here, let's look at DF2. So we're only looking at the row where DF is 2. That's the second row here. And we're looking for the chi-square statistic, 3.266, which is kind of between these two values. In fact, it's much closer to this one. So I might go ahead and just round it to 0.2, much closer to 0.2 than 0.15. So we'll say 0.2-ish. So from the table, our p-value, probability that chi-squared is greater than 3.266 is about, we said 0.2. Okay, and then let's go ahead and see what the calculator says. Good practice, right? Whole pointed notes. So we'll go second distribution manner, chi-square CDF from 3.266 to infinity with degrees of freedom 2, and I get 0.195. Which is very, very close to what we got with estimating with the table. And then I could go even further using my calculator and skip a whole bunch of steps. I could put this data into my lists and just do a chi-square goodness of fit test, and it'll give you an even more accurate answer. Okay? Either way, though, these two numbers definitely are not less than 0.05, which, oh yeah, I fixed that on your notes, but I forgot to stick it in here. So the third step here, which is on your notes, it says to state your significance test and your level, which I didn't add in here. Obviously, we did a chi-square goodness of fit test with degrees of freedom 2 and a significance level of 0.05. So since these two p-values, either way, are not less than 0.05, that means we fail to reject our null. Since our p-value is not less than alpha, we fail to reject H naught. What does that mean in context? That means we do not have enough evidence to conclude the proportions are different on Spirit Week. Okay, and that is correct. Okay, so the last part of this section is just kind of the step-by-step process using your calculator there. So if you want more information on all of that stuff, I went over pretty much all of it. Everything else that's on these next 2 pages it kind of goes over some more little tips and tricks we can do with the lists, as well as some things that we've done previously that you hopefully remember. If not, it's all right there. So I'll see you next time.